Hey everyone, I wanted to set the stage for some of the calorimetry problems we'd be working on over the next couple days. Now, I want to just quickly review the basic calculation for Q, right? This is our energy in joules, and that's typically equal to the mass of the solution or object times the specific heat capacity times the change in temperature of that object. Now, of course, mass is measured in grams. The specific heat capacity is typically has units of joules per gram degrees Celsius, and then delta T, right, has units of, degrees Celsius or K. Now, one of the things I want to point out is that all three of these units, right, bam, 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 right, two of those units cancel to leave us joules. So when we look at this, the units make sense. Really quickly, specific heat capacity is the amount of energy in joules needed to raise 1 gram of that substance 1 degree Celsius. Now, one question that comes up is sometimes I see this in K, not C, Kelvin. But because the temperature scales of Celsius and Kelvin, right? Kelvin is equal to whatever the degrees Celsius plus 273, right? Because these scales have the same, these two temperature scales, a 10 degree jump in Celsius is equal to a 10 degree jump in Kelvin because they differ only in this added value. This isn't true of Celsius and Fahrenheit or Celsius and Kelvin because with Fahrenheit the scale is different, right? Like with Celsius, water's boiling temperature is 100, its freezing temperature is 0, and that's a change of 100. In Fahrenheit, it's 32 to 212. That's not a change of 100. So you can't really make this equivalent in Fahrenheit, but you can in Celsius and Kelvin. A change of 10 in Kelvin is a change of 10 in Celsius. So you can use those interchangeably when we're talking about delta T's, right? The changes. That said, this is the master equation that we generally use. Now, you'll always be given the value for the specific heat capacity of a substance, with the exception of water. It really is good just to know that water has a value of 4.184 joules per gram degree Celsius. So that's specifically for water, and I just think it's useful to know because it is also the conversion between joules and calories, by the way. But it's just useful to know because water, aqueous solution, generally is how most chemistry happens. That said, what I like to do is I like to think of the following paradigm. Minus Q lost equals Q gained. Meaning, with calorimetry, typically we're measuring the heat lost of a reaction, and it's gained by the solution that the reaction takes place in. Now, to further sort of elucidate that, it's often broken down into minus Q reaction equals Q solution, SOLN, plus Q cal or Q calorimeter. Now, what this means is, and I'm going to use an exothermic reaction to explain this. If a particular reaction releases heat, and we're talking about our coffee cup calorimeter here. So let's say you just have some water, H2O, and you add some powder and you stir. And let's say this is an exothermic reaction. Because chemistry happens when bonds are broken and then bonds are formed, you may have a release of energy or an intake of energy. So let's just, for the sake of argument, say that it's going to be exothermic. So you can calculate the heat of a reaction simply by measuring the change in temperature and applying these two situations. In almost every single AP problem I've ever seen, QCal is basically said to be 0 or negligible. That said, I will include a problem that does use this term, but it's almost always excluded. So when we're doing calorimetry problems, they're often very simple and straightforward, where you simply have to answer how much heat is absorbed by this particular substance if its temperature changes this much. Now, of course, if we have the heat in joules and we have its mass and the change in temperature, what you might be asked to calculate is instead its specific heat capacity. So if you have 3 of the 4 variables, it becomes a plug and chug situation. It's just recognizing what it's asking you to do. A more complex scenario is when you are asked to measure the heat of a reaction that takes place in a calorimeter, where you start with this paradigm, right? Minus Q reaction equals Q solution plus Q cal. Now, this can be a little more complex, but we're going to work through some of these problems. And I'm going to basically, you've looked at some of these in your book, and I'm going to turn to some examples that you're going to be working through, and I'm going to look at these with you and kind of give you some starting places to go. So this is your problem set for homework. And I'm going to do a little bit of annotation for you so that you have some understanding about where to go. So remember, Q is equal to M times C times delta T. And then don't forget, sometimes that C is represented by a lowercase s. They both represent the specific heat capacity. So with our question 1, how much energy is needed to change the temperature of water, right, 50 grams of water by 15 degrees Celsius? Now, if it said 50 mils of water, remember that water has a density of 1 gram per mil, right? So 50 mils of water equals 50 grams. However, this scenario just tells us the mass, and here's where you do have to know that the specific heat of water is the specific heat capacity is 4.184 joules per mol K, or joules per gram degree Celsius, right? So that's the number, 4.184, and sometimes you will see it as 4.186, but most textbooks list it as 4.184 joules per gram degrees Celsius. Some problems will give you a slightly different value if it is a solution and not pure water. Use the value they give you, but if you're not given any value, even if it's an aqueous solution and you have nothing else to do, go with 4.184. And then in the next problem, how many grams of water can be heated from 20 to 75 using 12,500 joules. So in this example, right, where we have the joules, right, we have our Q that we're going to plug in, and we're going from 20 to 75. So we're not solving for Q in this case, right? We're just going to be solving for grams, and of course, we're still going to apply the 4.184 specific heat of water in that problem. What is the final temperature after 840 joules is absorbed by 10 grams of water? Here, instead of Q or M, we are solving. You can either put it, you can either solve for delta T and then plug it in over here with 25, or you can set up this equation, right? And then when you come to the delta T part, what is the final temperature absorbed by? You can put TF minus 25.0, right? Because it's always final minus initial. So, you know, you'd have your mass, you'd have your C, and then you have your delta T, and then you could solve for this variable. My suggestion is, rather than distributing the M and the C, divide out the Q by those values first. And then you isolate this side of the equation, and then rather than distributing your TF, what you're doing is simply moving your 25 over to the other side. It's a little bit easier. Number 4, the The heat capacity of aluminum is 0.9 joules per gram degree Celsius. Notice that the heat capacities of metals are much lower than that of water. And most rock is also lower than that of water. So this is why our Earth, which has a lot of water, has a moderate temperature range that when the sun goes down at night, the water, which held and absorbed a lot of heat energy during the day, slowly radiates it out at night, and this moderates our temperatures. That's why land near large bodies of water tend to go through less temperature extremes. If we're talking about a desert, right, with lots of rocks and sand and not a lot of water, you can have large temperature extremes because when, right, the heat when the sun goes away at night, you don't have the large bodies of water which have absorbed a lot of joules of heat, right? The heat capacity of rock is much smaller than that of water. So therefore, the rocks get hot and then they lose the heat quickly, and then they radiate the heat quickly, and then they don't have much of a moderate temperature throughout the night. So how much energy is needed to raise the temperature of an 8.50 times 10 to the squared gram block of aluminum? Again, similar to the other ones above, but we're going to be using a different specific heat capacity. Now in this next problem, it looks like what we're doing is getting a little more complex. I would think of this as one of those minus Q lost equals Q gained, and minus Q metal equals Q water. That's how I would frame this. Notice that this negative is going to have to be left in when we are doing this math. That said, try this math and you're going to see what I mean. If that negative is not there or you forget it, it will screw up the math of this scenario. So don't forget to add that in. And for the Q metal, right, we are going to use the mass of the metal, the specific heat of the metal, right? And, oh no, that's what we're calculating, right? So we're calculating the specific heat of this metal. And we're going to do it by using the heat energy absorbed by the water. In both of these cases, we are going to break these down into MC delta T, MC delta T. And something to note, right, that they're starting out at different temperatures, but this is the final temperature TF in both scenarios. And it's important to use that when you are doing your calculations, right? And it looks like by finishing reading this problem, what we're ultimately going to be determining, right, is the specific heat capacity of the metal. So we're going to be solving that value of C for that metal. In the next problem, in a coffee cup calorimeter, 100 grams of water and 100 grams of HCl are mixed. The HCl had an initial temperature of 46 and the water was originally at 24.6 degrees Celsius. After the reaction, the temperature of both substances was 31.3. Calculate how much heat the water lost or gained. So we're going to be looking at this just solely from the perspective of the water, and we're going to be using the Q equation for that reaction. Final answers are also linked on the next page so that when you do these, you'll be able to check your work. I didn't show the whole work, but I did give you the final answers, so you should be able to see if you're right or wrong. And then, of course, we can, I'm hoping to have, if I can find the time, I'll put the link up tomorrow, another kind of chat session, video chat session on Friday to maybe do some review for the AP exam, another FRQ. So that's a time you could also ask for some clarification on those problems if you didn't get them. Okay, so, or you can just send me an email and perhaps I can help out a little bit sooner than that. I hope this helped, and good luck with these problems. I will talk to y'all soon.